The microcontroller on the Arduino Uno has an analog to digital converter. This allows you to sample analog signals. Well, what if instead you want to generate an analog signal? Some microcontrollers have what's called a digital to analog converter. The Arduino Uno's microcontroller does not. Instead, it can simulate analog signals using a method called pulse width modulation. So in today's lesson, we're going to learn about pulse width modulation and then apply pulse width modulation to modulate the colors generated by an RGB LED. Let's get started. So what exactly is pulse width modulation, or PWM for short? Simply stated, it's a way of modulating or changing a digital signal to make it simulate an analog signal. Let me show you a picture to show you what I mean. If I were to plot a digital signal which oscillates between 0 volts and 5 volts, I may get something that looks like this. So you can generate signals like this with the microcontroller on the Arduino Uno. And what makes it digital is the output here is either low, 0 volts, or high, 5 volts, and nothing in between. In pulse width modulation, what we do is we modulate the amount of time that the signal is high. Call that T on. Could call it T high, but let's call it T on. We modulate that amount of time relative to the amount of time that the signal is low. We'll call that T off. Now, whenever you have a signal that oscillates and periodically returns to the same place, moving in the same direction as it was before, we can call the amount of time it takes for the oscillation to occur the period of the signal, or capital T for short. So when you have a digital signal like this, another name for a signal like this is a step function. When you have a signal like this, the period is equal to the sum of T on plus T off. Okay. What I'm saying is, in pulse width modulation, we modulate T on. We can change the amount of time that the signal is high relative to the period of the signal. So that allows us to define something called the duty cycle. The duty cycle is equal to the amount of time the signal is high, T on, divided by the period, which in this case is T on plus T off. And to convert this into a percentage, it's customary to multiply by 100. So you get the duty cycle as a percentage. Okay. So I'll talk in a minute about how can a signal like this simulate an analog signal. But first, let me draw a couple different pulse width modulated signals with different duty cycles to illustrate the point. Here's a pulse width modulated signal with a duty cycle of 0. It spends no time high and all the time low. So this pulse width modulated signal is essentially the same as digital right low. There's nothing. Voltage of 0. Here's a pulse width modulated signal with a duty cycle of 100%. The signal is always high. It's always 5 volts. This is equivalent to a digital right high. Alright, so those are the two extremes. Duty cycle 0%, duty cycle 100%. Let's look at some examples in the middle. So here's an example where T on is equal to T off. This would give you a duty cycle of exactly 50%. The signal is on 50% of the time and off 50% of the time. Well, here's an example where the signal spends 1 unit of time on and 1, 2, 3, 4 units of time off. So the period of the signal is 5 units of time, and it spends 1 of those units high. So the duty cycle would be equal to 1/5, or 20%. the signal spends 20% of its time high and 80% of its time low. All right, so how does all of this allow us to simulate analog signals? Well, a bit that I left out here is that these oscillations are carried out very quickly, on the order of 1,000 times a second or more. And so in many circuits, for all intents and purposes, the circuit is essentially not seeing high and low, high and low. It's essentially experiencing the average voltage over a period of time. So up here, when you have a duty cycle of 50% oscillating between 5 volts and 0 volts, the circuit in some situations is essentially experiencing half the peak voltage, an average voltage of 2.5 volts. Down here, with the duty cycle much lower at only 20%, the external circuit is experiencing about 20% of the peak voltage, 5 volts, which is 1 volt. Okay, so the average voltage, or the voltage averaged over time, is oftentimes what the external circuit experiences, and that's what allows us to simulate an analog voltage, a voltage that's graded and can be anything between 0 and 5 volts, using a digital signal. Okay, so the next thing I'm going to do is I'm going to build a circuit composed of a RGB LED, and then we're going to play around with this circuit using pulse width modulation. So when I get to the Arduino IDE, I will demonstrate the lines of code in the sketch that allow you to generate pulse width modulated circuits. Oh, there's one more thing I didn't say. Only certain pins, only certain digital outputs on the Arduino Uno are capable of generating pulse width modulated outputs. They are pins 9, 10, and 11, and pins 3, 5, and 6. And you can tell which pins are capable of pulse width modulation because on the Arduino board, they have little wavy symbols next to the numbers. All right, I'll point that out later in the video. All right, I'm back in the Arduino IDE, and I've set up a sketch here with a setup function and a loop function. And I've defined 3 bytes, red, green, and blue, corresponding to the 3 pins, 11, 10, and 9, to which the 3 LEDs in my RGB LED are connected. So pin 11 goes to the red LED, 10 to the green, and 9 to the blue. And then in the setup, I've designated, using a pin mode command for each one, that all of these pins are going to be used as outputs. Now remember, these pins are also capable of pulse width modulation. That'll come into play later. But let's take a look at what happens if let's just do a digital write on the red pin to set it high. Upload it. And we get red. All right, if I do that on the green, we get green. All right, so the cool thing about RGB LEDs is you can combine numbers, or combine colors. So what color will we get if we turn the red and the green LED on at the same time? Does anybody know what you get when you mix red and green light? These aren't pigments, these are light. So by the laws of additive color mixing, you get yellow. Anybody guess that? What color do you get if you mix blue and red? You get, anybody know? Magenta. Magenta. All right. It's a little hard to see. Maybe I can bend it a little bit. There we go. It's so bright. All right. So, but we just learned about pulse width modulation. And so what pulse width modulation allows us to do is, you know, blue, let's just turn on the blue LED. And it's pretty bright. All right. That's too bright. We want a blue light, but we don't want it that bright. Maybe we only want it to be 50% as bright. So instead of using a digital light, we can use an analog light. And then the analog light command creates a pulse width modulated signal on the blue pin, pin 9 in this case. And so it takes two arguments. The pin that we want to control and create the pulse width modulated signal on, and then it also takes a number between 0 and 255. And a 0 would correspond to a duty cycle of 0%. 255 would correspond to a duty cycle of 100%. And you can go anywhere in between. So if I do analog right blue 255, the blue light will turn on and it'll be just as bright as it was before. If I do 0, the blue light will come on and it'll be, well, it doesn't come on because a pulse width modulated signal with a duty cycle of 0% is always off. What would be a duty cycle of 50%? What number should I put in here? It's the whatever's halfway between 0 and 255, which is about 127. So here we'll get a blue light that's about 50% as bright as it was before. If I put 25 in here, that's a duty cycle of about 10%. It's going to be even dimmer. Put a 3 here, that's a duty cycle of about 1%. You can barely see, it's on, but not very much. Okay, so analog lights and pulse width modulated signals, they allow us to simulate analog outputs. And in this case, that means we can drive the LED to produce light in a graded fashion. Instead of all or nothing, we can produce light of varying levels. At least we perceive the light to be emitted in varying degrees of intensity. Okay. So you can do more fancy stuff. So let's make the LED here do something that's kind of like breathing. Have you ever seen the LED on a MacBook when it is asleep? It kind of turns on, gets brighter, and then it gets dimmer. So we can do that with a for loop. So we'll define an integer x, and we'll give it the initial value of 0. But then in this for loop, as long as x is less than or equal to 255, we will increment x by 1 each time through the for loop. So I can do that, or I can do x equals x plus 1. And I'll do an analog write on the blue pin, but in this case, the argument that specifies the duty cycle is going to be x. So the first time through the for loop, it's going to be 0. The next time it'll be 1. The next time it'll be 2, all the way up to 255. So let's upload this and then see what it looks like. Well, it doesn't look like much. It's happening too quickly. Let's put a delay in there of 10 milliseconds. Now you see the light gets brighter, 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 and then turns off and it starts over again. This is more like gasping than breathing. So I can add another for loop. And this one will increment X in the opposite direction. It'll start at 255 and go down to 0. All right, upload this. So now it'll look like the blue light is getting brighter, and then after it gets as bright as it's going to be, it gets dimmer, and the process repeats. I can get more fancy here. So the cool thing about RGB LEDs is you can combine colors. So maybe as the blue light is getting brighter, I want the, let's do the green light will get dimmer. So I can do 255 minus X instead of X in the analog, right? And down here, while the blue light is getting dimmer, let's make the green light get brighter. All right, let's upload this. So this might be hard to see in my camera, but blue and green together make cyan. Let's do red and green instead. I think that'll be more noticeable. So what this should do is cycle through from red to yellowish orange to green and then back through the color spectrum back to red. Cool, pretty cool, right? So there's thousands of different combinations of red, green, and blue values you can create using one RGB LED and pulse width modulation. So that's it for the lesson for today. In class, we'll get out an oscilloscope and I'll show you a pulse width modulated signal in real time, and I'll prove to you that it is in fact a step function. But again, the cool thing about pulse width modulation here is that when we drive the RGB LED with a pulse width modulated signal, we can create what appears to be an analog light intensity. We can create the intensity of light on that's more graded than all or nothing. We can create the perception of light intensities between all the way on and all the way off. All right, I'll see you next time.